cardiac contraction and the steps involved in cardiac contraction in this video, doctors. So, basically cardiac myocyte is a striated muscle, right. So, the way striated muscles are arranged, if you could see the basic histology, the striations are formed by a perfect alignment of thick and thin filaments, doctors. So, as we saw in nerve muscle physiology, because of a proper architectural orientation of thick and thin filaments, we tend to get striations in myofibrils. So, the contraction of both the striated muscle looks absolutely similar except for a few key differences that we will be seeing now. Okay. So, other than that, the contraction process taking place in a skeletal muscle and a cardiac muscle are more or less same, doctors. Okay. So, let us take up the myocyte cell. So, just like a skeletal muscle cell, the cardiac muscle cell also do have the same kind of T tubules, right. But the only difference is instead of instead of having a neuromuscular junction, these T tubules are going to connect themselves. These T tubules are going to connect themselves with neighboring cells through gap junction. So, the cations of one cell can be very easily shared with the neighboring cell through gap junction, so that every single cardiac muscle becomes excited at the same time and they can able to contract as a syncytium, right. So, here we have got a T tubule. Now, in this T tubule we have a channel on the wall of T tubule called as dihydropyridine receptor. So, we have a channel on its wall called as dihydropyridine receptor. Dihydropyridine receptor is nothing but a voltage gated L type calcium channels, Now, if you consider the key difference between a skeletal muscle and a cardiac muscle, cardiac muscles, cardiac myocytes have got poorly developed sarcoplasmic reticulum. They have got very poorly developed sarcoplasmic reticulum. So, the purpose of sarcoplasmic reticulum we all know, right. Sarcoplasmic reticulum is nothing but a storehouse of calcium. Since cardiac myocyte lack well formed sarcoplasmic reticulum, they cannot able to store calcium in a significant way, which is essential and which can be adequately supplied for contraction of that particular muscle fiber. Since a cardiac myocyte cannot able to store calcium adequately, it is dependent on extracellular fluid calcium, right. So, to get those extracellular fluid calcium, we have a separate kind of channel on the T tubule called as dihydropyridine receptor that brings calcium from the ECF in a greater quantity into the cytoplasm than happening in a skeletal muscle. So, calcium from extracellular fluid enters cardiac myocyte through dihydropyridine receptor channels. The calcium moment it enters into cytoplasm of a cardiac myocyte, the calcium goes and binds with another channel which is nothing but a ligand gated channel called as ryanodine receptor channel. Ryanodine receptor channels is a ligand gated channel which is located in sarcoplasmic reticulum. Whatever the available trivial amount of sarcoplasmic reticulum is there, they will have little bit of calcium stored in it, and the opening of that particular calcium stored sarcoplasmic reticulum is governed by a channel called as ryanodine receptor, which is a ligand gated calcium channel. So, the ligand for this channel is calcium itself. Calcium is the ligand for the ligand gated calcium channels. So, calcium from ECF gets into the cytoplasm, combines with ryanodine receptor, opens it up, so that stored intra-sarcoplasmic calcium, whatever trivial it is, comes into the cytoplasm. This calcium, the moment it enters cytoplasm, goes and binds with a protein called as troponin C. Troponin C binds with calcium. This makes the troponin C to undergo modification. So, this modulates troponin T Thereby, troponin T moves away, moves tropomyosin from binding sites. This leads to interaction of actin and myosin filament. This leads to cardiac contraction. Doctors. This is how cardiac contraction takes place. Right now, one thing to be remembered, please understand, the calcium required for cardiac myocyte contraction comes predominantly from extracellular fluid and to some extent from sarcoplasmic reticulum. When I say some extent, you can even consider that as a trivial extent. Okay, so if a cardiac myocyte, once the contraction is over, if it has to relax, it has to send the calcium back to the place from where it is coming, which means majority of calcium has been pumped back into extracellular fluid, right? The task of getting the calcium back to the extracellular fluid is done by a transporter called a sodium calcium exchanger, which is a secondary active transporter, guys. So you have sodium calcium exchanger, which is a secondary active transport. As you know, secondary active transport is extremely dependent on functioning of primary active transporter, which is sodium potassium ATPase. So there will be pumping of 3 sodium for exchange of 2 potassium into the cell. As 3 sodium gets out, that sodium is used for taking sodium inside the cell. As sodium gets into the cell, there will be efflux of calcium. Thereby the muscle goes for relaxation. That is the primary way cardiac muscle goes for relaxation. Pushing the calcium into the sarcoplasmic reticulum also do happen, no doubt in it. But the extent and the magnitude of calcium outflows primarily back into extracellular fluid through sodium calcium exchanger. Now this pump, sodium potassium ATPase, if it has been blocked by digoxin, doctors, there will not be efflux of sodium. When sodium efflux doesn't happen, it is not utilized for influx to get calcium out. So because of absence of sodium efflux by sodium potassium ATPase, there will not be calcium efflux from sodium calcium exchanger. Thereby all the calcium is going to stay in the cytoplasm itself, increasing cytoplasmic calcium level, increasing the amount of calcium available to bind with troponin C, thereby enhancing contraction. That is exactly how digoxin increases. Cardiac contraction. Digoxin increases cardiac contractility, doctors. Now this is a double jackpot actually. You know digoxin is prescribed in conditions called as congestive heart failure, isn't it? Where the cardiac pumping mechanism has been impaired. So in congestive heart failure, we have two risky areas which can compromise the patient's cardiac function and can drive the patient into instant cardiac arrest and death. Number one is poor cardiac perfusion, cardiac arrest, and the second one is tremendous oxygen demand. You know that when the heart's architecture gets distorted as a kind of compensation, there will be LV or RV remodeling, isn't it, doctor? As a consequence of remodeling, right, when the architecture of heart distorts, the pumping activity tremendously falls. That puts the heart muscle into a serious state of stress. In order to contract against such a stressful condition, the cardiac oxygen demand tremendously increases. So even a trivial fall in oxygen supply to cardiac myocyte can put the patient into myocardial ischemia. He can or she can land up in myocardial infarction also. So these two, one is pump failure and the second one is myocardial infarction, are the two most important conditions that can drive a CHF patient into instant cardiac arrest. Now, if you put this patient on digoxin, on one hand, you are increasing the cardiac contractility. On the other hand, since you are blocking sodium potassium ATPase, you are reducing oxygen demand of the tissues. As oxygen demand of tissue reduces, the chances of development of ischemia and infarction has been tremendously brought down. That is how digoxin is a lifesaver in case of congestive heart failure patients, doctors. So, that is our cardiac contraction. Okay, that completes our cardiac contraction. Now, the point to be noted here is, be very thorough about the molecule called as troponin, right, doctors? So, troponins are have got three components: troponin T, troponin I, and troponin C. While troponin T binds tropomyosin, troponin I binds actin, troponin C binds calcium. Out of all these three molecules, troponin T is extremely important because with every cell necrosis, okay guys, with every cell necrosis and cell breakdown, troponin T is released. As well as you have release of creatinine kinase MB subtype, right? So, you have both troponin T as well as creatinine kinase to be released into circulation because of cell necrosis. These are all what we used to call as cardiac markers. These are all nothing but cardiac markers. Now, what is the importance, doctors? What is the importance of cardiac markers? These troponin T as well as creatinine kinase MB that we colloquially call as TROP-T as well as CKMB, both these molecules increases in 3 to 6 hours after infarction. 3 to 6 hours after infarction, which means if a patient comes with acute chest pain within minutes, when you suspect a acute chest pain and when you suspect a myocardial infarction for a case of acute chest pain, and would you like to go for troponin T markers assay, do not go for troponin T markers as well as CKMB at least less than 3 hours, right? Because those 3 hours will not have enough amount of troponin T as well as CKMB in the circulation good enough to be detected by all our conventional biochemical assays. So, till 3 hours has been passed, there is no point in doing CKMB or troponin T because their levels will not simply be elevated in serum by the time. So, that is point number 1 you got to be very familiar with on troponin T and CKMB. Number 2, while creatinine kinase MB falls within 1 to 2 days, of infarction, troponin T remains elevated for about 1 to 2 weeks of infarction. Remember, troponin T remains elevated to up to 1 to 2 weeks of infarction. So, if you go for serial assessment of troponin T, you could still able to find increased troponin T till a duration of 1 to 2 weeks, doctors. That is very important. Now, the most crucial point here is when you suspect reinfarct in a patient, in a previously MI affected patient, right, there is no point in going for troponin T elevation, which is why CKMB, creatinine kinase, is the best marker of choice, right, doctors? When you suspect reinfarct, you thought you have treated the MI, you have thrombolized it, you have made the vasculature patent, everything was fine, patient was shifted to ICU, CC, or you could have even stepped the patient down. And when you suspect a reinfarction, there is absolutely no point in going for assaying troponin T because though the infarction is cleared off or not, it does not matter. Troponin T remains elevated in serum for a period of 1 to 2 weeks, right? So, the best marker in such a conditions is CKMB, doctors, right? So, this is the cardiac muscle contraction and the proteins associated with cardiac muscle contraction and their importance. So, that completes our cardiac contraction.